Good. Thank you, Tim.
And
Okay.
I think you might need to stand on this side, right? Is that where you?
Yeah, from this camera over, they can see.
Oh, okay. All right. All right, it's my pleasure to introduce Chuck Huber. He's the Director of Statistical Outreach at the Stata Corporation, also an adjunct associate professor of biostatistics at Texas A&M School of Public Health and at NYU School of Global Public Health. In addition, he works with the Stata team of software developers. He produces instructional videos, several of which I've seen are really quite good, for the Stata YouTube channel. He writes blog entries, develops online net courses, and gives talks about Stata at conferences and universities. And we've kept him busy in this area. He's been in Duke and State and RTI, doing lots of presentations. He's published in the areas of neurology, human and animal genetics, alcohol and drug abuse prevention, nutrition, and birth defects. He currently teaches survey sampling at NYU and introductory biostatistics at Texas A&M, where he previously taught categorical data analysis, survey data analysis, and statistical genetics. Today's talk is one that should be quite useful to us at CPC. It's an introduction to survey sampling using Stata. So thank you, Chuck.
Oh, thank you for having me today. So just out of curiosity, how many of you work with survey statistics already? You actually do analysis with survey weights? See, that's what I was worried about. So for most of you, you might could just go grab lunch. This is going to be at a very introductory level, although you may learn a couple of little tricks along the way. So I am going to try and move fairly quickly. I tried to shorten this because we're going to try and leave plenty of time for questions. And the clicker's not working, so I'm going to stand over here. Oh, now the keyboard's not working either. There, the mouse works. There we go. So if you want to download the slides and data sets and do files for today's presentation, you can grab those at tinyurl.com/survey sampling intro. And so what I wanted to do, just in case we run out of time, is put everything in one slide, everything you sort of need to take away from this. And so to work with survey data that contains survey weights or complex sampling designs in Stata, the first thing you're going to need to do is survey set your data. You call it survey set, it's svyset, and that's how you tell Stata about the details of your sampling design. And once you do that, everything else becomes pretty straightforward. If you want to calculate a mean of something, you just put SVY : in front of that, and it will adjust your mean for the survey weights or whatever stratification or whatever else you've done. If you want to do this for a subpopulation, this is an important line right here. Don't use if. When you're working with survey weights in Stata, don't use if. Sometimes you can get away with it and it works, but sometimes it won't. So just get in the habit of using SVY, subpop, for instance, white female, if you had an indicator for white female, colon, and then estimate your sample. You can do tables the same way, SVY : tabulate. If you want to fit a regression model, SVY : and you fit your regression model. You can still, if you're familiar with Stata, you can still use the margins command, but you'll need to add the VCE unconditional option, and then things just work. So we've made it remarkably simple, at least in my opinion, to work with survey weights. Oh, shoot. I changed my slides this morning. There's supposed to be another slide after that. I'm using the wrong slide deck. Okay, back to the old slide deck then. This doesn't have the multiple imputation stuff in it. It's too late to change the slides now. We'll talk about multiple imputation later, but I don't have slides in the one I sent over earlier. So I usually begin with this somewhat provocative slide because I think it makes us stop and think about why we're using survey weights to begin with. And the whole point, at least in my opinion, of doing these complex sampling designs is because a random sample is not necessarily a representative sample. And I usually enjoy this argument because I do have a good example of why this is true. If you go to a casino in Vegas and someone deals you a royal flush, I guarantee you that deck is very well shuffled. It's a random sample, but that royal flush is not a representative sample of the deck of cards. So a random sample is not necessarily the same as a representative sample. And what we often really want, we say we want a random sample, but what we really want is a sample that's representative of the population that we're interested in. So that's the goal of survey sampling, is to come up with a nice representative sample. So let me show you what can go wrong without using a representative sample. So let's say I have a population that's exactly 50-50 males and females. And the height of males and females is usually different. So the average height of the males in the population might be 160 centimeters, and the average height in the females may be 151. So if they're 50-50, if we do the weighted average here, half of the sample is 160, half the sample is 151, we get an average height in the population of 155. But what happens if we draw a sample that's 25-75 males and females? Well, the sample is no longer representative of the population. And so let's say that I do happen to get a sample where the height in the sample is 160 centimeters for the males, and it is exactly 151 for the females. So the sample contains the right numbers, but the wrong proportion of males and females. When I calculate the average height for the entire sample, it's 153, and I'm off from the population. So that's the problem with having a sample that's not representative of the population. You can end up with numbers that are inaccurate. They don't accurately represent the population. So one of the key features of survey sampling, and I know this is a review for at least half of you, but sometimes it's worth reviewing these things. Part of what we're used to doing in statistics is dealing with what are called non-probability samples. We just draw a sample and we don't really know the size of the target population or the sampling frame from which that sample is drawn. We know the size of the sample though, and so we just go about calculating, various statistics and confidence intervals and p-values. But we never really know the probability that any particular individual sample. Survey sampling, on the other hand, deals with probability samples, in which case we're very careful about defining our population, our target population. And since target populations are often theoretical things, we generally have to operationalize that as a sampling frame. So the target population is the thing we want to learn about. But the sampling frame is the sort of the population we're actually able to define. In the old days, there were things like phone books. I don't think they make them anymore, but say you wanted to know something about the population of Chapel Hill, you could go get a phone book for Chapel Hill that enumerates everyone with a phone in Chapel Hill. And from that phone book, you could draw a sample. So you would know the size of the sampling frame, big N, and you would know the size of your sample, little n. So you could calculate the probability that any individual makes it into the sample. So that's probability sampling, and that's one of the features of survey sampling. So what I want to do today, and it's going to be long, and I'm going to have to skip a lot of slides because I have the wrong slide deck here, but I'm going to go through and review some of these sampling concepts in the context of setting up Stata's survey set command, because the first thing you have to do is tell Stata about the design with the svyset command. So we're going to go through that svyset command and talk about what these things are in it, and then I'll show you some quick data analysis examples at the end. I'm going to be using the NHANES, part of the NHANES data set. This is the National Health and Nutrition Examination Survey data. I believe this is the 2015-2016 wave we're going to be working with. I have a lot of extraneous slides in here that I removed from the one I was going to use today. But anyway, the punchline of this is that these data are just floating around on the web freely. You can go out and grab these without having to fill out any forms or any kind of IRB approval. They're just sitting there on the web, and so you can go get this. So if you want to learn something about these kinds of data, this is a great place to go get it. And I'm going to skip over some more things here. You can import these data directly from the web into Stata. They're stored as SAS transport files, and you can just put the URL of the data set you want right into your Stata command and import it and merge the files and do all of your data management. And again, without having to fill out any forms or register or get IRB approval for these things. So the first thing we need to do to work with survey data, especially the NHANES data, is fill in this dialog box. You don't have to use the dialog box, but we're going to use it as a visual aid to tell Stata something about our sampling design. So this is the svyset dialog box, and it contains inputs here for the number of sampling stages, the primary sampling units, the strata, finite population correction factors, and sample weights. So many of you are probably familiar with these terms and what they mean, but for those of you who aren't, we're going to go through and explain these, and for everyone else, it'll be reviewed. So the first thing here at the top are the number of sampling stages. What do we mean by that? I'm going to skip through a bunch of slides here because I have removed these up to here. So what do we mean by sampling stages? Well, rather than just going out and finding a bunch of random people, What we're going to actually do is sample them in stages. And the way this is done with the NHANES study is they begin in the United States by sampling counties. So they actually sample 15 counties. So you imagine throwing all 50 states in a hat and pulling out 15 counties names from the hat. So stage one is randomly sampling the counties, the counties from within the states. Then from within the counties, they're going to sample segments. These could either be like voting districts or school districts or statistical SMSAs. I always forget what that stands for. But at stage two, we're going to randomly sample from within the counties, and then from within the segments, we're going to randomly select households, and from within the households, we'll select people. But that's again one of the hallmarks of these complex sampling designs is these multi-stage samples. And it's random at each stage. It's not systematic. We're randomly selecting at each stage, but we need to account for that when we go and do our statistical analysis later on. So as a quick example, now my slides are not in the same order. Anyway, we'll come back and talk about sampling weights a bit. So the next thing we need to specify once we tell it the number of sampling stages is we need to tell it the primary sampling units at each stage. What is the thing that we actually sample? So in NHANES, they sampled the counties first, and then the census, we're going to call them census blocks next, then the households, and then the people. So we have those ID variables in our data set. For instance, the counties, we have 15 of these counties, so they're all sampled, and if we tabulate them, we'll see there are 15. So we're going to put those variables in each of these boxes here, and they have to be in the correct order, or things will get messed up. Stata will throw errors. Okay. So that's where the primary sampling units are going to come from and where the stages come. Okay. So next up are stratified samples. So sometimes we want to stratify to make sure that certain groups are represented. So I mentioned this right out of the gate that a random sample isn't necessarily representative. So let's say that we have a population that's roughly 50-50 males and females and has roughly equivalent numbers of people at each age of 15, 16, and 17. But we draw a sample and the proportions of females and males at each age group are not the same. So again, this can screw up our inference about the population if we don't adjust for this in some fashion. So one solution to this problem is to draw a stratified sample so that the relative proportions of males and females in each age group in the sample match the population. And so you can do that by, for instance, if I said I need 50 males that are age 17, I just sample 17-year-old males until I get to 50 and then I stop. It's still random, but I'm just going to stop when I get to 50 or whatever number I want within each of these strata. Same thing then with the 16-year-old females. I'm going to stop when I get to 50 or 100 or whatever, however many I need in each of those particular strata. So that's why I would want to use something like stratification. So in the NHANES example, I might stratify the counties by small counties and large counties. And then once I sample the counties, I might then stratify the census blocks as rural and urban. And then once I sample the census blocks, then within households, I might sample single person households or multi-person households. And then at the individual level, I might stratify by males and females, just to make sure that I get a representative sample for each of these categories. So at the county level, I might have a variable, a strata variable per county. And so 0 might indicate small counties, 1 might indicate large. Census might be 0 as rural, 1 as urban, and so forth. You can read the rest. So I have these strata variables in my data set, and I'm going to put those in each of these boxes then under strata. And of course, they have to match the correct sampling stage. So county strata has to go with stage 1 with the county primary sampling. You just have to make sure you put these in so that they all match. Now, the finite population correction factor, I'm going to skip over some bias slides here and talk about finite population corrections. So what's that all about? Well, I mentioned earlier that most of the statistical methods we've learned about deal with non-probability samples. And so we don't really know the probability that any individual is sampled. But in our studies for survey samples, we need to know that. So we're going to define a sampling frame such that we know the number of people in the sampling frame and we know the number of people in the sample. So we can calculate the probability that any one individual in the sampling frame makes it to the sample. And it's just little n divided by big N. So the next thing we need to take into account is the fact that we're sampling with replacement. Normally, we don't think about such things. We just go about it and don't think, well, am I sampling with or without replacement? So just as a quick review, what do we mean by sampling with replacement? So if I have a bucket of 10 balls, 2 of them are red, 8 of them are green. The probability then of drawing a red ball is 2 out of 10. Probability of green ball is 8 out of 10. This kind of makes sense. So if I draw a red ball and I sample with replacement, that means I'm going to sample the ball, but then I'm going to put the ball back in the bucket. So the probability, the next time I draw a ball, the probabilities are the same. There's still 2 out of 10 for red and 8 out of 10 for green. So that's sampling with replacement. What happens if I draw a red ball without replacement? Well, initially, the probability of drawing a red ball is 2 out of 10. But if I don't put the ball back in, let's say I take the ball out and leave it out, the probability of drawing a red ball is now changed. It's now 1 out of 9 because there are only 9 balls left and only 1 of them is red. Well, then let's say I draw a green ball, the probability of drawing a red ball is changed again because the denominator changed. Now it's 1 out of 8. So every time I draw another ball without replacement, it changes the probability of any one element being sampled. And if you think about that, that's what we do with human beings or other things that we sample in scientific surveys. We might not really think about it explicitly, but if you're, in the old days where you stand in a mall with a clipboard and you want to talk to people, if a person walks up that you've already sampled, you don't go and ask them to do your survey again, you already got them. So whether you realize it or not, you're sampling without replacement. So the idea of the finite population correction factor is that we're correcting for the fact that we've sampled from a finite population without replacement. And so we're going to call it the FPC for short. This is defined then as big N, the size of the sampling frame, minus little n, divided by big N minus 1. So why do we care about this? Why is this thing important, this FPC? Well, it's going to correct for some things for starters. If you were to write out the variance, each of the major sampling designs has its own variance and its own bias, and the math gets kind of complicated. And if we write it out in pieces, so let's say we want to calculate the variance of a sample mean for a simple random sample, we have the variance, and then the bias is usually why we subtract off the minus 1 in there. But the variance for a complex sampling design is also multiplied by the FPC. And if you do some arithmetic and reduce some things, the variance left is this little formula here. Well, why do we care about any of this? Let's say that I'm sampling from a known population size of 100,000. If I draw a sample of size 50 and I ignore the FPC, the standard error, let's say in this case is 0.4472, some number I pulled out of the air. And for a sample of size 50 from a population of 100,000, the FPC is 0.9995 if you calculate it. And I multiply that times the standard error, I end up with 0.4471. Well, that's not very different for a sample of size 50. But as the sample size increases, that FPC gets smaller and smaller. And since I'm multiplying the variance times that FPC, it's shrinking the variance, okay? So the larger my sample is relative to the size of the population, the smaller my variance. Well, we generally like to do that because the smaller the variance, the smaller our confidence intervals, the smaller our p-values, and so that's generally considered a good thing. And so we typically, not always, but we typically calculate this with survey samples because we have that information. We know big N and we know little n, and so it's easy to calculate this. So as you can tell from the table, for small samples, it's not very important, but for larger samples relative to the population size, it becomes important. There's actually a little book called Statistical Rules of Thumb, and one of those rules of thumb in that book is that the FPC really only becomes useful in terms of variance reduction if the sample size is more than 10% of the size of the target population. So that's when it really kicks in and can start helping you out. And if you're doing power calculations, this can also help you out. So if you've done your power calculation and it's like 0.78, like, oh no, I need 80% power, you might think about using the finite population correction factor because that might be enough to help get you to 80% when you're doing your power calculations. Okay. So you're going to need these variables in your data set though. Someone has to have done this calculation, either you do or someone else has to have done these calculations. And it has to be done at each sampling stage because each sampling stage has its own sampling frame and its own sample. So you're going to be able to calculate this at each stage. So I have 4 of these in here: county FPC, census FPC, and so forth. And then I would simply put those in the dialog box here, and that becomes part of the sampling features in my data set. So I'm moving kind of quickly because we wanted to save the questions for the end. Normally I like to take questions along the way, but I think we're going to take them all at the end today. So I'm just going to move along. Sample weights. So where do these things come from? And this often I think is a mystery as to how are these things calculated? Where do they come from? So again, back to the notion of, I make use of this slide a lot, I know, but back to the idea that we have a well-defined sampling frame of size big N, and I'm going to draw a sample size of little n. I'm going to have that at each stage, at each sampling stage. So let's say within Haynes, I have 15 counties and I want to pick one of those 15 counties. So I pick county 7. So I've sampled one county out of 15 here. So the probability that that one county is sampled is 1 divided by 15 or 0.0667. So that's the probability of that particular county being sampled. Its sample weight then is going to be the reciprocal of that probability that it was sampled. Well, in this case, that's simple because 1 divided by 15, the reciprocal of that is just 15. Okay, 1 divided by the probability of being sampled. So what that essentially means is that that one county is representing 15 other counties in the population. That's what that sampling weight means in terms of its interpretation. So let's go to sampling stage 2, the census block. So let's say that I sampled 25 census blocks out of a total of 360 census blocks. So the probability that any one of those census blocks has been sampled would be 25 out of a total of 360, so 0.0694. So that's the probability that any one of those census blocks is sampled. So the sample weight is just the reciprocal of that. So 1 divided by the probability of being sampled in this case is 14.4. So again, an interpretation of that weight is that each of those census blocks that were sampled represents 14.4 other census blocks in the larger population. Okay. And I think you get the idea. At each stage, I'm going to have to calculate this. I'm not going to go through the arithmetic for the last 2 stages, but I think you get the idea. Here, each household that's sampled represents 11.5 households in the population. And if we sampled 1 out of 8 people, each person that's sampled is representing 8 people in the population. So that's how these sample weights can be calculated, and that's how you would interpret them if you were just looking at the sample weights and what they mean. So once I've calculated them or somebody else calculates them, you can put them right here in the dialog box. And again, you would need 1 at each stage. And now Stata knows about the sample weights, and it will incorporate that into any statistical calculations that it does. So the next piece of the puzzle here that we need to tell Stata about is the variance estimation technique. Now I'm really frustrated. I brought the wrong slides, but I have a better screenshot of this. But so there are a variety of choices: linearized, bootstrap, BRR, jackknife, SDR, and there's one other under here that I'm forgetting. BRR is right there. Anyway, there are a collection of these, and the question then becomes, which one do I use? So I'm assuming you're the data analyst, not the person designing the study. If I'm the data analyst, well, which one of these should I select? Well, unfortunately, I've taught this over the years quite a few times, and there is no, oh, here we go, SDR, successive difference replication. There are 5 of these in Stata that you could use. There, as best I can tell, there is no rule of thumb or some collection of decision tree you can go through. If this, then use linearized, or if this, then use bootstrap. It's very specific to the sampling design, and often it's built into the sampling design. I can't think of a better way to say it. It is part of the sampling design. And so the best advice I can offer you for selecting a variance estimation technique is read the manual. Whoever designs these things has put a lot of thought and care into how they've designed the study and collected the sample. And they will tell you what variance estimation technique to use. So be sure to read the instructions. There's actually a chapter in the manual on NHANES about how to do the variance estimation technique. And there are different ones for different scenarios, and they explain it in the manual. They also, in the NHANES manual, they also tell you the survey set command to use with the data set. So you don't even have to go through and understand all of this stuff necessarily to use the data set. Just go read the documentation, and it will tell you right there, use this svyset command, and then you're ready to roll. Okay. So I would select, most of the time, NHANES uses linearized variance estimation, so I would select linearized, click OK, and it's going to issue this giant command. So that would be the command, svyset county, strata, FBC. These little triple slashes at the end of each row tell Stata that the command continues on the next line. So this is all one giant svyset command. Now, any of you who've worked with the NHANES data, let's look at some data examples now. Any of you who've worked with the NHANES data know that that's not the actual data you get. They don't give you all 4 stages of sampling. That's how they collected the sample, but for privacy reasons, they collapse all 4 stages into one stage. And so this is the example data that we're going to run through. The actual svyset command for the NHANES data looks like this. It's just svyset PSU. Strata is just the variable strata. Weight. Sometimes you use the weight MEC. That's the mobile examination center weight. Other times you use the lab weights. We're going to be using the linearized variance estimation, and single unit missing refers to if a particular strata only has one sampling unit, we're going to treat it as one. So for the NHANES data, this is actually what the svyset command would look like. Again, for privacy reasons, they don't give you all 4 sampling stages and all of that information. It's been collapsed into to a single stage. So I've accumulated a bunch of variables. I pulled them down off the website and merged them all together. So you, if you download that zip file, you've got a bunch of data you can play with. And I thought I'd go through, there's some biological data in here. There's some smoking and drug use questions in here. I downloaded the depression questionnaire. This is all in one big data set, so you don't have to go to the web and merge it if you want to play around with this data set. So let's just go through some quick examples of things you can do once you've applied the svyset command. If I want to calculate the average age and apply the sample weights, I just put SVY colon in front of my mean command, and it will calculate the mean age, accounting for the features of the survey design. So at the command, for the command, I just need SVY colon. If I look at the output, notice that it tells me the number of observations and the population size. Because again, with survey sampling, we're very explicitly drawing inferences about a specific population from which the sample was drawn. And so essentially the population size then is the sample size multiplied each observation. It's the sum of the sample weights is what it is. So in this case, we're talking about the United States, probably circa 2000 to early 2000s. So the population size is about 316 million. So we get our mean and our linearized standard error and a confidence interval. It's really easy to estimate a mean that way. If I wanted to estimate the mean age over race, for example, I can do that again by just using my usual mean command and putting SVY colon in front of that. And that gives me an estimate of the mean age in each of the categories of race, again, along with its standard error and confidence interval. If I wanted to do this, there's a glare on the screen. If I wanted to do this by two variables, race and female, again, I just type SVY colon in front of my mean command, and it gives me a table that takes all the survey weight information into account. Now, subpopulations, this is important if you do a lot of work with survey weights and Stata. It's tempting to use if. So you could type mean age if race equals 2 and female equals 1. You could do that, and you might get away with it sometimes. Sometimes it does work and sometimes it doesn't. The problem is that if isn't smart enough to reweight things. Sometimes it needs to do some adjustment to the weighting when you restrict it to a subsample. And so in general, I would recommend you just forget about the if command when working with survey weights and always use the subpop option. And so you could put, it is possible to put just race equals 2 and female equals 2 inside the subpop option for SVY. You can do that, but I've kind of gotten this weird habit of defining my subgroups as an indicator variable and then putting those in the subpop option. It's up to you, but either way will work. But the main thing you should not do is use if. Don't type mean age if race equals 2 and female equals 1. Do it this way with the subpop option. Okay. Now, tables, same thing. I just put SVY colon in front of my tabulate command, and again, it will show me the proportions in each of the groups, along with the number of observations, population size. I can do cross tabulations and get statistics in here, statistical tests. I would not recommend using these uncorrected tests. Use the design-based test. I'm not entirely sure why we put the uncorrected forms in the output. I think it's just for curiosity's sake. But anyway, so you can do cross tabulations and do tests that account for the survey weights. You can also do linear regression by just putting SBY colon in front of your regress command. So if how many of you are familiar with Stata? Have you used Stata? Okay, almost everyone. For those of you who haven't, I guess I'll pause and explain what this cryptic syntax means here. The C.age sharp I dot female. That's a shorthand way of telling Stata that I would like to see. Sorry, there's a glare right on that where I'm standing. That's a shorthand way of saying I'd like to see the main effective age on SPP, systolic blood pressure, treating age as a continuous variable, and I'd like to see the main effective female treated as a categorical variable. That's what the I dot tells Stata. And I'd like to see the interaction of those. So I want to see the main effective age, main effective female, and the interaction of age and female also. So it's a shorthand way of writing that. So I can fit this regression model, and again, it accounts for all the survey features of the data set. Now, what's really handy is after I use my survey prefix on regress, I can still use Stata's margins command to estimate predictions from the model. So I could type margins female at age 20 through 80 in increments of 10. So I want to see separate regression lines for males and females. And I want to see the lines plotted at age 20, 30, 40, 50, 60, 70, and 80. So that's what this at age 20, 10, 80 means. It's the beginning of the interval, the ending of the interval, and then the increment size. Now, if you do this with survey weights, though, you need to be sure and specify the option VCE unconditional in your margins command. Okay, it won't do that automatically. Just because you use SBY colon here, it won't automatically apply that. It will automatically take all the survey weighting into account, but you want to specify VCE unconditional at the end of your margins command. But other than that, then you can type margins plot and do your margins plots, just like if you were fitting any other kind of regression data. So SBY prefix and VCE and conditional, you're back in business with margins. This is really handy, in my opinion, with logistic regression models or Poisson models, things that are not linear, because I can type SBY colon in front of this and use the margins command to get predicted probabilities. So the vertical axis here is the predicted probability of diabetes. Okay. So rather than having to look down this column of odds ratios, and someone asks, well, how do you interpret that odds ratio for the interaction of age and female? Would anyone like to try that? Anyone want to take a crack at interpreting an odds ratio for an interaction term? Yeah, me either. But if I use margins and margins plot, it's really easy to convert that to the probability, predicted probability of diabetes. And so it's nice to be able to just look at these curves over age and see that females tend to have a lower probability of diabetes, and that gap between males and females is larger for older ages. So again, even if you have complex survey weights, you can still use margins and margins plot. Structural equation models, even generalized structural equation models, can account for survey weights. So let's say that I want to fit a generalized structural equation model for depression. So depression is my latent variable here, and I have these 10 indicators of their various questions. I don't remember the exact questions. I thought I have them listed in here somewhere, but I don't. But things like have trouble sleeping, feel sad and blue, those kinds of questions. I can take those questions and create a scale using a latent variable here for depression. And then I might want to see how depression influences overall health status or things like that. Even for very sophisticated models like this, I can fit those accounting for the survey weight. So I can type SBY colon and then use the GSIM command to fit this fairly sophisticated structural equation model. So not only can I get my output here, my path coefficients, I can even use the predictions to generate plots of these. So this might, on the horizontal axis here, this might be a Z-score for depression, their overall Z-score for depression. So further to the right means more depression symptoms on the questionnaire. Further to the left means lower depression. And then I can go through and look at health status by the depression score. So for instance, if I look at excellent, this dark blue line here is excellent. If I have very low, if my score is very low on this depression scale, my probability of having reporting excellent health status is higher. As my score on the depression scale is higher and higher, the probability of reporting excellent health status goes down. Similarly, poor, if I look at this bright red line, that's for reporting poor health status. For low depression score, the probability is low. As my depression score goes higher, the probability of me reporting poor health status increases. So I can graph the results of this, even accounting for all the survey weights. So I had some slides. I redid these slides after I sent them, and I forgot we were going to be using them on here. If you want to do multiple imputation, I don't have the slides, so I'm going to have to wave my hands and you're going to have to use your imagination. There's a variation of svyset called MI-SVY-set, MI space SVY-set. And once you do that, you can then impute your variables using MI-impute and MI-estimate. And there are a bunch of other MI commands. I had some slides that show how to do that, but they're on my laptop and now we will set that up quickly. But just be aware, if you do have issues with missing data and you want to do multiple imputation, you can do that in the context of survey weight, or do that with survey weights, and you have to just use MI-SVY-set rather than plain old SVY-set. So sorry about the confusion with the slides. The other slide deck had one of these examples. So believe it or not, I'm finished 5 minutes early. I was told to be done by 12:45. So any questions? I'd show off some of my favorite books in here. One is the Valiant and Deaver. This is written for, they wrote this for the State of Press, our publishing arm, and it has a lot of information on post-weighting, techniques like rating and things like that, adjustments for non-response and things like that. So that's available through State of Press. I've taught survey sampling at both Texas A&M and NYU, and this is probably my favorite textbook simply because it has lots of cool examples. It's got a lot of breadth and it's very applied, and it's also fairly up to date. I can't remember when the second edition came out. 2017, 2018. So if you're looking for one-stop shopping, I highly recommend this book as a good place to start, especially if you're using Stata or SAS. A lot of the examples are either in Stata or SAS. And then there's the good old Levy and Lemeshow if you're in the planning business of these kinds of studies. And then there's the Corning-Brevard if you're in the analysis of this. This contains a lot of great examples, but it is a bit more theoretical. Yeah, question.
Thank you so much. So first, just technically, are the slides available to us? Will they be?
Yes, so at tinyurl.com/survey sampling
Okay.
intro. And I can send you, if you'll email me, I'll send you the version I meant to use today, not the normal version, because we were going to try and squeeze this into 45 minutes instead of an hour to an hour and a half. So I pulled a bunch of the minutia out and put in some stuff about MI. So I can send you the other version.
And then back to the comments on the multiple imputation. So I always think it's a great tool to use because, you know, we're trying to generalize to population, and if we, you know, get rid of observations along the way, I always worry about what that does to our estimates. But at the same time, it's always hard to know, like, how much data should we impute, or, you know, can you talk, I mean, just from your experience on using multiple imputation in Haynes or whatever, kind of rules of thumb you think about when you're doing multiple imputation, just some guides for us.
Did you tell him to ask this question?
Oh, but
Okay.
it's right there.
I thought you know the answer. Oh, you, okay. The reason I ask is because I had a student a master's student who asked this exact question. How much data can we impute? And that came about from a study I worked on a long time ago using the FARS data, the Fatal Accident Reporting System. I'll try and make this a short story, but it gets to the answer to your question. So anytime there's a fatal accident in the United States, whether it's in the car or pedestrian, if there's a fatality involved with a car accident, it must be reported to the federal government, and it goes into the FARS data set, Fatal Accident Reporting System. And I was doing some work with collaborators with this data set, and one of the variables we were interested in is the blood alcohol level of the driver. 80% of the blood alcohol data were missing. 80% were missing. We only had 20% of the data. And the group that maintains this data with feds imputed 80% of the data from 20%. And when I first saw that, I thought, that's insane. You can't, no, you can't do that. And at first my knee-jerk reaction was to refuse to use it. But I started kind of reading through the methods section because it's, again, it's one of these federal data sets that comes with a manual. And I read through the manual. I thought, you know, these are some really smart people who spend a lot of time on this imputation. I guess I'm going to have to trust that they know more about what they're doing with this than I do. So, okay, I guess I'll go along with it. So we did it. And we published the paper, and I don't even remember the details anymore. It's been 15 years ago, but that kind of haunted me for a long time. That should I have done that? Should I put my foot down and said, this is insane? Well, then the student named Jim Long wanders into my office years later. And he was working on his master's degree, and he was very interested in multiple imputation. I don't know why, but that was his thing. And so I said, I have an interesting project for you. I have an interesting idea for your thesis. Let's do a simulation study and see how much data can we impute and get away with it and recover the correct parameter estimates. And so that's exactly what we did. We simulated complete data under a variety of scenarios, and then we systematically went through and knocked out 10%, 20%, 30%, all the way down to 90%. We even went beyond 80%. So we would impute 90% of the data from the remaining 10% of the data. And we did it for varying sample sizes and changed a bunch of things around. And the shocking thing was, honestly, my goal was to show how foolish this was with the farce data, that this should have never been done. That was kind of my intent. And lo and behold, and we ran it several times and checked it because I just didn't believe the results, but even imputing up to 80, 90%, as long as you had a reasonable sample size of that remaining 10, 20%, we were recovering correct parameters of known data. So we would start with known data and knock it out. So we knew the truth and impute it. It works. Now, the where it works is if the remaining 10% sample size is fairly large. So you couldn't do that with 10 or 20 people. But the fatal accident reporting data was tens of thousands of observations. And so they were imputing, yeah, they only had 20% of the data, but that 20% was still thousands of observations. So they had plenty of data for imputing the other 80%. And as long as we had reasonable sample sizes remaining, we had pretty good luck recovering the parameter estimates. And I have his thesis somewhere. We never got around to publishing it. He ended up going to medical school instead of staying with statistics.
Oh, that's too bad.
But I was shocked. I was honestly shocked. So does that answer your question?
Well, yeah, but then I worry about the selectivity too, so it's if the people who are missing on, because of certain kinds of characteristics. Do you have though, are those part of your multiple imputation
Considerations.
Yeah.
Sure. So quick review of missing data mechanisms. So there's sort of missing completely at random, where it's just so completely random, it has nothing to do with anything with the data set. And then we're just doing this morning, missing at random, where the missing data is not related to the thing you're interested in, your outcome, but you may have information in the data set that contains information that the example we were using this morning was college GPA, missing college GPA data. And parents' income is associated with college GPA. And so you could use information contained in parents' income and maybe high school GPA to impute missing college GPA data. So, and then there's the missing not at random, where the reason it's missing is because of the thing itself. So maybe income data or drug use data. They're not reporting their drug use because they use drugs and they don't want to report that. So the mechanism of missing this obviously plays a role in the choice to do imputation. I know you know this, but other people often choose to reweight. So for data that are missing, I'm blanking on the term. Anyway, some people do choose to use reweighting for things rather than using multiple imputation. There are other techniques. But imputation is a possibility. And one of the things I've learned from teaching this for Stata has a paid course. We have a whole course in survey sampling also. And I'm shocked that people who do this and work with survey weights aren't aware that you can do multiple imputation with survey weighted data in Stata, and it's actually pretty straightforward. Yeah.
Do you know any citation you need to publish that paper or because I don't know of any, even from Ruben or Alice or others of the big imputation people, they don't have a rule of thumb of what you have a citation that
I can send you Jen's thesis.
yeah.
We were going to publish it, and he ran off to medical school and just kind of got caught up in other things, and so we never bothered to It seems like I've seen another study though that has done something similar, with similar results. So,
I think some of the work on the multiple imputation has talked about how we may have been imputing too few data sets to get accurate results. And,
right.
rather than the 5 or 10 or something like that, we should go to higher numbers. I've seen things on that.
Yeah, but what I have found with reviewing papers of people, sometimes they want to impute 50% of the
Yeah.
sample. Reviewers say it's too much, like your reaction.
Yeah.
And there is no, I don't know of a citation that can say it's okay up to the impute rate. There's also, then you have the problem of how large is your sample, how much power you have.
Mhm.
So it's,
Yeah.
it's hard to.
And the other variables you have in the data set to use for the imputation, that makes a
That's
difference as
variable.
well. Yeah. I'll see if I can find a citation, but they're not gonna take some guy's thesis as evidence.
But then you, it's published.
We should, I hear from Jen every once in a while, that's been 12, 13 years ago, but he's
That'd be
a
really
physician
very
somewhere.
important.
Yeah, I wish we had published it, but so many hours of the day, and it was his thesis, so I'm not really comfortable publishing without him being involved. So. Maybe someday.
So I had a question, and this is,
Yeah.
what are the common commands you can't do with SVY? Because there, I mean, I've
that's
been
a good
using SVY
question.
for a long time, and sometimes I learn something new because I was like, oh wait, you can do that now? You know, but there are lots
Yeah.
of things you can't do.
So unfortunately, you can't do anything that has to do with likelihoods, log likelihoods. So likelihood ratio tests go out the window. AIC and B, no, yeah, AIC and BIC go out the window. Do they? No, I think you can do, I don't remember, but I do know likelihood ratio tests go out the window because I come from a biostat background and that's just, well, that's what we do, likelihood ratio tests, and you can't do them with survey weights. So you have to do the test and test parm commands as a way of getting around them. Other commands that don't work. I know IRT works with it because that's some form of GSIM. It's a rapid command of GSIM. SIM works with survey weights. Well, there are others, but I can't really
Well, I
think
mean,
of any.
I mean, there's some of the basic ones, like you can't do just, you know, like summarize or.
Right, no, those are old
Yeah.
commands, things that are really old in
Yeah.
Stata, like summarize and
I'm dating myself then.
yeah, no, I mean, old in Stata, they've been in Stata since version 1.
Yeah.
Summarize goes all the way back to version
Yeah.
1. Somewhere I have a copy of Stata version 1, and it's weird to see the things that were in there from the very beginning. But anything to do with likelihood ratio tests, there's something important that I'm just blanking on. But most of the things that I would do with it works with survey weights. The table, have you played with any of the reporting commands, the collect and table commands?
Not recently.
Those are really cool. In Stata 17, now I'm sounding like a commercial, but in Stata 17, we really went all out on our reporting features. So there's the new table command. There's always been a command called table in Stata, but it got a complete overhaul. It behaves very differently than it used to now. And you can create very pretty customized tables and you can collect things. Anyway, when I tried to teach that stuff with my survey sampling students last fall at NYU, and it doesn't play too well together with the weights just yet. It's still brand new and some of the table features don't play well. If you have survey weights and tables and then you want to collect the information from that and send it into a table, that is still a little, it could use some improvements. But the main things it doesn't work with is anything that has to do with a log likelihood, specifically likelihood ratio. Can anyone think of something?
I think that VIF, we cannot use them, some of the assumptions.
Yeah,
I'm sorry, what did you say?
variance of
But
VIF.
there is such inflation factor and I forget which one. But at some point I was looking some of the assumptions and Data couldn't do it by our hand, but I don't remember which. But, it's difficult to do.
The thing is, A lot of any commands that begin with ME, like ME logit and ME Poisson and those sorts of things, if it begins with ME, it's actually running GSIM as the computational engine. And since GSIM works with survey weights, then all of the ME commands work with survey weights. All the IRT commands are using GSIM as the computational engine. So, oh, I know, Bayes. Nothing in Bayes works with the survey weights at this point. I can't say definitively it will at some point, but I'd be shocked if it didn't at some point. But Bayes is still a fairly new thing in Stata, and so, but at some point, I'm sure we'll incorporate the ability to use survey weights with Bayes, but right now you can't. So anything Bayesian. Have you guys played with the Bayes prefix in Stata? Yeah, so you can type in front of almost anything now, regress, logit, whatever. Most Stata commands now, you can type Bayes colon in front of the command and it sidesteps the maximum likelihood engine and runs it through MCMC. And you can customize the priors and all that, but at its most basic, you just type Bayes colon in front of regress or logit or whatever, and it runs it through the MCMC engine, and you get posterior means and posterior standard deviations. Incredible. And none of that works with survey weights. So, yeah.
First, Tim, are there any questions from remote?
Oh,
And I don't see any questions in the chat, but if anybody online has any questions, you can unmute and ask your questions. We can hear you fine.
Yes, I have a question. Can you hear me?
Yes, Gustavo.
Yes, thanks for the presentation. I wonder what are your thoughts about the use of sampling weights in regression analysis? And I ask because there is this school of thought, particularly in economics, that if you include covariates related to the sampling design, it is not necessary to include sampling weights.
I'm not sure I understood the end of the first part of your question. So incorporating sample weights into what? I'm sorry?
Into regression analysis.
As another explanatory variable.
Oh, using the weights themselves as an explanatory.
No, it's to using the sampling weights in a regression analysis, because some people think that by including covariates related to the sampling design, that is enough and there is no need to use sampling weights.
So you mean if you're controlling for race and age and gender already, do you need the weights or metro, or is that what you're asking?
Yes.
I'm just talking off the cuff. I haven't really thought about this or read much on it, but I would say yes, you still need to apply the sampling weights, even if you're adjusting for the covariates, because you're adjusting for them. But what if the sample is not representative of the population? The whole purpose of the weights is to make sure the sample is as representative of the sample as possible. And then the interrelationship, I'm waving my hands so you can see me. And then whatever interrelationships in terms of mediation or moderation or those sorts of, for lack of a better word, distortions between the variables, those are two different issues. One is making it representative, the sample representative of the population. The other is getting at the interrelationships among the variables.
I understand.
That's my thoughts off the top of my head, but
I understand. What I mean is covariates that are related to the sampling design.
Oh, covariates that you've pulled in from somewhere else. These are completely external from.
No, from the sampling design. Let me write it in the chat.
Okay. I don't think I'm understanding your question correctly. Somebody want to rephrase it?
Well, if you have the variables that go into determining the weight and they're already in the analysis,
Okay.
sample weights are not necessarily needed because you're controlling for what went into the weights. And there's diagnostic tests to see if it makes any difference whether you use the weights or not.
Right. Sometimes you can omit the weights and you still get lucky and you still end up with the same parameter estimates.
Well, you don't have to depend on luck other than probability. In the sense
Right.
that you have diagnostic tests that you can perform just to see if the coefficients are significantly different,
Sure.
whether you have the weights or not.
Right.
And there's an advantage because when you use the weights, the standard errors are a lot larger than they would be without the weights.
Sure.
So there's diagnostic tests to see if you need to use weights.
Yeah. Yeah, that still feels a little creepy to me, but yeah, I can see why you would want to do that if you wanted to get your standard errors down. But again, the weights are there to make the weights are there so that the sample is as representative of the population as possible. And what it sounds like is in certain scenarios, the sample without the weights just is. So it'd be like if your sample happened to be 50-50 male and female, and your population is 50-50 male and female, then it doesn't make a difference whether you use the weights or not.
I
But
guess
if
I
you
should
skip the
preface
weights,
my
then you get
comments that I'm talking about in the modeling situation. If you're
Okay.
doing descriptive statistics, like a
Yeah.
nice summary, then most definitely you want to use the weights.
Okay,
But if it's a modeling question where you're testing hypotheses,
yeah,
there are diagnostic statistics that you can see whether it
sure,
makes any difference
yeah.
to have the weights in.
Is that the question? Oh. okay.
Yes, that's the question.
Okay.
You
Good
have a
advice.
paper on
Various
You have paper.
sampling. See, I think that's the covariates related to the sampling design. Is that like strata variables that you used in stratifying? I'm not sure what that means.
Anything that goes into making up the weights. Any variable that's used to predict what the weight should
But the weights are calculated by the sampling design, by the sampling stages. So like being male and female, unless you stratified by that, it wouldn't be part of the sampling design. So is that what you're saying? If the strata variables, should those be used as covariates?
Yes, if you use your sampling design is on the basis of geographical place, size of the city, and then you use that to calculate the weights, and people think that you can instead use covariates.
I just have never really thought about that. I don't know. I'm just going to plead ignorance on that one for now. I don't know. I just haven't really thought about that. It sounds like you have. Do you have a good answer for that one?
I have the same understanding.
Okay.
That if you have the covariates that go into the weights that
You
need to
don't
use.
include the weights. Okay.
Is it possible for those not to be part of your survey sampling though, that you still look at survey commands for clustering or something? I'm just trying to think of,
Well, the weights come from these characteristics that go into the sampling.
yeah.
And if you have those variables already part of your
Yeah.
covariates in the analysis, then it's usually not necessary to have the weight in there.
I also think it might depend on what type of estimate, because you have to deal with collapsibility of the measure. So if you're using traditional regression techniques and you have a non-collapsible measure, like an odds ratio, you have to use inverse probability of treatment weights to get like a marginal estimate.
Yeah, that, I think we'd have to write some of this out, but we do have to end it. I got
Oh, yeah.
the cut-off signal here, but we can continue, conversations afterwards. So, thank you so much.
Oh, thanks for having me. Sorry, I skipped the wrong slides.